Hey everyone, and welcome to this explainer. I am honestly so excited to be diving into this with you today, because we are looking at what is arguably one of the most fascinating engineering challenges of our entire lifetime. We are taking a journey through the sheer, massive scale of solar engineering. We're going to trace exactly how human ingenuity captures the power of the sun, starting from those relatively simple residential water heaters, all the way up to those massive, totally sci-fi looking power towers sitting right in the middle of the desert.
But right off the bat, we've got to address the elephant in the room, the central paradox of solar energy. On one hand, it's a completely fantastic resource, right? It's totally free, it's non-polluting, and there is virtually no limit to how much of it we could theoretically use. But here is the catch, and it's a really big one. The actual rate of solar radiation hitting any single square foot of the Earth is, well, it's pretty low. The energy is literally everywhere, but it is incredibly dilute. So to capture enough of it to actually power our lives, you usually need massive surface areas, which obviously requires a ton of space and capital. Plus, it's intermittent. It vanishes at night and hides behind clouds. Capturing a resource that is both extremely dilute and intermittent, that demands some seriously brilliant engineering.
So how do we solve this dilution problem? Well, we basically break it down into three main methods. First, there's the heliothermal process. That's capturing and concentrating heat. Second, the helioelectrical process, making direct electricity. And finally, passive solar, which is basically just really smart architectural design. Let's go through these, starting with the most common one.
All right, Section 1. Heating water with flat plate collectors.
This is absolutely the simplest, most widespread active solar application anywhere in the world today. It's actually amazing how common these systems are globally, especially in places like Southern Europe and Asia where, the sun is shining more than 200 days a year. What these are Thermosiphon solar water heater systems. They're incredibly cost-effective, often costing $1,000 or even less, to completely meet a family's daily hot water needs. And honestly, the best part, they run on purely natural circulation. As the water inside the collector warms up, it naturally rises into a storage tank, and the heavier, cooler water just sinks right back down to get heated. They can easily produce hot water at temperatures just under 80 degrees Celsius.
If we mentally peel back the layers to look at the internal anatomy of one of these flat plate collectors, it's beautifully simple. You've got a basic box enclosure covered by glazing, usually just one or two layers of standard glass. Beneath that is a very dark absorber plate. The glass lets the solar radiation in, and that dark plate just eats it up, trapping the heat. Attached directly to that plate are little flow passages. So as water runs through those parallel tubes, it absorbs the heat straight from the metal. The whole unit is heavily insulated on the back and the sides, so the heat doesn't just leak back out into the surrounding air.
Moving right along to Section 2, concentrating heat for power. This is where we scale up for industrial electricity.
Now, a flat plate collector works perfectly if you just want a warm shower. But what if we need to, say, power a whole city? We need way higher temperatures to drive heavy industrial machinery. And to get those insane temperatures, we have to leverage something called the concentration factor. Because sunlight is so dilute, we basically have to act like a giant magnifying glass. The concentration factor is simply the ratio of the large aperture area, meaning the large field of mirrors collecting the widespread sunlight, to the much smaller receiver area where all that light is being focused. By funneling a massive amount of light onto one tiny target, we create an optical multiplier effect. That's how we generate extreme industrial-grade heat. Take the parabolic trough collector, for instance. These are those massive, curved mirrors that capture the sun and reflect it directly onto a single linear receiver tube that runs right along the focal line of the curve. By doing this, we can heat the fluid inside that tiny tube up to a scorching 400 degrees Celsius. That superheated fluid is then piped through a heat exchanger to boil water, create extremely high-pressure steam, and spin a giant steam turbine that's hooked up to a generator. Out in California, there are parallel rows of these troughs generating literally hundreds of megawatts of grid power.
But listen, if you really want to see this sci-fi scale of solar engineering, you've got to consider the Ivanpah Solar Thermal Power Plant out in California's Mojave Desert. It is absolutely huge, occupying roughly 3,500 acres. It's a solar-powered tower design, and it represents a massive, game-changing leap in how we concentrate solar energy.
To truly wrap your head around the scale of Ivanpah, just think about this one staggering number, 300,000. That is the number of individual, software-controlled mirrors, they're called heliostats, that sit out in the desert, actively tracking the sun across the sky and reflecting its light perfectly under receivers sitting way up on top of 140-meter-high towers. It's wild.
And the way this huge 377-megawatt facility actually works is brilliant. All 300,000 of those heliostats focus their light on a solar receiver boiler at the very top of the tower. Water flowing through the pipes inside that boiler absorbs this intensely concentrated energy and just instantly vaporizes into superheated steam. That vapor gets blasted straight down into a turbine located at the base of the tower. Interestingly enough, Ivanpah actually uses an air-cooled condenser, meaning it uses about 95% less water than traditional wet-cooled thermal plants, which is crucial in the desert. Now, Ivanpah itself doesn't store energy, but it's definitely worth noting that other tower plants, like Gama Solar in Spain, heat up molten salt to 900 degrees Celsius. That salt holds onto heat so incredibly well that it can keep the turbine spinning and pumping out electricity for up to 15 hours after the sun goes down.
Okay, Section 3. The magic of photovoltaics. Direct helioelectrical generation.
Pivoting completely away from catching thermal heat and boiling water, let's talk about solar cells. Unlike those massive, loud, spinning turbines, solar cells generate electricity directly. Zero moving parts. How? It's all semiconductor physics. Usually, you take silicon and dope it with phosphorus to create an N-type semiconductor, and dope it with boron to create a P-type semiconductor. When you sandwich them together, they form a PN junction. The second sunlight hits this junction, it literally excites the electrons, inducing an immediate electrical current directly across the gap. It is such an elegant, silent way to turn light straight into usable electricity.
There is a downside, though. A single, standard commercial silicon solar cell only gives you about 1 to 2 watts of power, running at maybe 15 to 20% efficiency. So how in the world do we power anything with that? Well, we scale it. Individual cells get wired together to form a module, which is just what we normally call a solar panel. Then you connect a bunch of modules together to form an array. Because of this incredible modularity, photovoltaics can scale from a tiny little setup on an RV all the way up to massive interconnected grid arrays covering entire fields.
Which brings us to Section 4, designing with the sun using passive solar applications.
Let's bring things back down to earth for a minute, to the absolute oldest, simplest method out there, just designing smart. Passive solar requires no mechanical pumps, no high-tech electrical circuits. It relies entirely on architectural engineering. A really brilliant example of this is the Trombe wall, named after a French professor, Félix Trombe. It's usually a very thick, dark-painted masonry wall built on the south-facing side of a building, with a layer of glass mounted just on the outside. During the day, that thick stone absorbs the sun's heat. Because there are little vents at the top and bottom of the wall, cool room air gets sucked into the bottom vent, warms up in the gap behind the glass, and naturally rises back into the room through the top vent. It creates this totally free, natural convection heating loop. And then even after sunset, that thick wall just slowly radiates its stored thermal energy into the house all night long.
Of course, the most common passive solar feature any of us interact with is just a standard window. But, as any engineer will tell you, not all windows are equal. We measure a window's efficiency using the Solar Heat Gain Coefficient, or SHGC. This metric is absolutely crucial. It's the total fraction of the sun's radiation that actually makes it through the glass and into the building. Get this, a standard 3mm thick pane of clear glass transmits a massive 86% of solar energy right indoors. So, depending on whether you're trying to survive a freezing winter or a sweltering summer, picking a window with the right SHGC is going to drastically alter your heating or cooling bills.
When sunlight actually hits that clear window glass, the physics are pretty interesting. The radiation doesn't all just pass straight through. About 8% of it just bounces right back outside as reflection. Another small chunk, about 6%, is physically absorbed by the glass itself, physically warming up the pane. But the vast majority, that 86%, shoots straight indoors. Once it's inside, it bounces around, gets absorbed by your furniture, the floors, you, and turns into sensible heat. So the total solar heat gain of your room is that transmitted light, plus whatever heat the glass itself absorbed and is radiating inward.
So that leads us to a pretty fascinating final thought for this explainer. We've just seen how we can capture natural heat on a roof, boil water with mirrors in a desert, excite tiny electrons in a silicon cell, and even trap warmth inside a masonry wall. The sun is essentially an infinite, completely non-polluting nuclear reactor that just showers our planet with free energy every single day. So, I want to leave you with a quick challenge. The next time you step outside, just take a look around your neighborhood. Think about how much free, highly usable energy is just bouncing off the roof of your own home right this second, completely untapped, just waiting for the right engineering to capture it. Thanks so much for joining me on this explainer. Catch y'all next time.